Okay, get this. What if I told you that a single type of molecule is the secret link between life-saving surgery, your favorite perfume, and even starting your car on a cold morning? Well, today, we're going to pull back the curtain on chemistry's ultimate unsung hero.
So this molecule is a total chemical chameleon, right? It's a key player in these wildly different parts of our lives, but it just hides in plain sight. So how does one simple atomic setup manage to wear so many different hats? Seriously, just think about it for a second. What on earth could possibly connect early surgical anesthesia, the complex scent of a perfume, and the fluid that helps your engine kick over on a freezing day? I mean, it seems impossible, but the answer is hiding in a single, really elegant piece of chemistry.
I mean, the range here is just wild. On one hand, you've got diethyl ether, which completely revolutionized surgery as an anesthetic. And on the other, something like anisole, which gives perfumes their unique fragrance. This same family of chemicals is also used as an industrial solvent, a refrigerant, and that starting fluid for engines. How can they be so different, but also so connected?
And the answer to this whole puzzle, well, here it is. It's a molecule called an ether. This simple but super elegant chemical structure is the common thread tying all of these different uses together. And it's all about that central oxygen atom acting like a bridge. All right, so we've cracked the case. It's the ether. But what exactly is an ether? Let's get into the nitty-gritty. Let's look at the actual blueprint that gives it all its power. You know, at its heart, the structure of an ether is it's really simple. Just picture an oxygen atom acting as a bridge between two other groups. Chemists label these groups as R, but they're basically just collections of carbon and hydrogen atoms. And the simple ROR structure, that's the signature of every single ether out there, no matter how simple or complex it gets. But here's a cool detail. That connection, it's not a straight line at all. The two R groups hanging off the sides are kind of bulky, and they actually push each other away, creating this slight bend in the molecule. This specific angle isn't just some random trivia. It's absolutely fundamental to how the ether behaves and interacts with the world around it. Okay, so we know these things are super useful, but how do you make one? Well, there's a classic recipe for it, but it's a bit of a high-stakes game. If you get it right, you get your ether. But if you get it wrong, you end up with something completely different. Well, the go-to recipe, is called the Williamson Synthesis. It's a method so reliable it's used to make everything from industrial solvents to life-saving drugs. Think of it like snapping two Lego bricks together. You start with two main ingredients, an alkyl halide, which is just a carbon chain with an atom that's easy to pop off, and a sodium alkoxide, another carbon chain attached to an oxygen. You heat them up, and click! They snap together perfectly to form that ROR ether structure. It's a really beautiful and efficient process. But, and this is a huge but, there's a catch. The shape of your starting materials is everything. For this to work, you absolutely need to use a simple, less crowded halide and a more complex, bulky alkoxide. If you try it the other way around, with a bulky halide, the whole reaction just fails. The molecules are too crowded to snap together right. Instead, a piece gets knocked off and you're left with a totally different molecule called an alkene. So yeah, in this recipe, your choice of ingredients is absolutely crucial. All right, so building them is one thing, but how do you break one apart? I mean, these are pretty stable molecules, so cracking that strong carbon-oxygen bridge requires some specific, really powerful tools. Well, you need some serious chemical crowbars for this job, and those crowbars are strong acids, specifically hydrogen bromide or hydrogen iodide. They're pretty much the only things reactive enough to actually break that tough CO bond. And of the two, hydrogen iodide, or HI, is definitely the more powerful option. And the whole thing goes down into really neat steps. First, the acid gives a proton to the ether's oxygen, which basically activates it for the next step. Then, in step 2, the halide ion, that iodide or bromide, swoops in and attacks one of the carbons next to the oxygen, breaking the bond and splitting the ether right in two. Okay, but wait, if you've got two different R groups, one big and one small, how does the halide know which one to go for? Well, it's simple. It takes the path of least resistance. It will always go for the smaller, less crowded carbon group. It's kind of like trying to get through a doorway. You'd pick the one with fewer people blocking it, right? Chemistry loves to be efficient. All right, let's bring it all full circle. Let's connect this chemistry back to that very first question we asked. What is it about this simple ROR structure that gives ethers all their unique little superpowers?
And really, it all boils down to one word: polarity. Remember that bent ORO shape we talked about? Well, because of that bend, one side of the molecule ends up slightly negative and the other side is slightly positive, kind of like a tiny, weak magnet. Chemists measure this imbalance. They call it a dipole moment, and this tiny bit of charge is the secret to almost everything an ether can do. And you can literally see the effect of this right here. Take a look at this table. Diethyl ether boils at about 34.6 degrees, which is almost the same as pentane, a molecule with a similar size. But now, look at the alcohol, butanol. It boils at over 117 degrees. So what gives? Why the huge difference? Well, alcohols can do something called hydrogen bonding. They stick to each other really tightly, making them much harder to pull apart into a gas. Ethers can't do that, so they evaporate easily. And that's what makes them so volatile and so great as starting fluids for engines. But here's the really cool part, the final little twist in the story. While ethers can't hydrogen bond with each other, that polar oxygen atom can form hydrogen bonds with water. And this is the key to why they're soluble in water and why they are such amazing solvents for a huge range of things. They've really got the best of both worlds, low boiling points, but good solubility. So when you think about it, this simple ROR bridge in an ether is responsible for an incredible array of functions that literally shape our world. It kind of makes you wonder, doesn't it? What other simple atomic arrangements are out there, quietly acting as the secret building blocks of our reality? Thanks for joining me on this deep dive into the world of ethers.